Second hypothesis test that we're going to look at revolves around a car dealership. The car dealership wants to test whether they've set the number of miles on their 2-year warranty correctly. They currently cover 30,000 miles, and they want to test if their clients use an amount different than 30,000 miles in their first 2 years of ownership. So from that, I have to pull out my step 1, which is a null and alternative hypothesis. In this case, the alternative hypothesis is given to me from this line where they say they want to test if their clients use an amount different than 30,000 miles. They don't say they're trying to see whether they use more or they use less. They're leaving either open. For that reason, the mean is not equal to 30,000 should be my alternative hypothesis. My null would then be the mean is equal to 30,000. Step 2, we need to pull out the information in order to calculate these test statistics. So the first thing that I see is the dealership collects mileage data for 150 new car drivers. They got the data from 150 people, so that's going to be our sample size, or our N150. They drove an average of 32,000 miles in their first 2 years. That's going to be our average from the sample, or the X-bar, 32,000. If the standard deviation is known to be 10,000 miles, sigma equals 10,000. Is there sufficient evidence that the mean number of miles driven in the first 2 years is different than 30,000 at a 0.01 level of significance? That last line is a little different than how we saw it before. Really, this is equivalent to saying they want to be 99% confident. In the Cengage system, they ask it both ways, so I have it written both ways. Basically, if they tell you level of confidence, you need to do 1 minus that level of confidence to find your alpha. If they say it like they do here at a 0.01 level of significance, you can just record that 0.01 as your value of alpha. So now that I have everything needed to calculate my test statistic, I'm going to calculate it. Z equals X bar, 32,000, minus the mean under the null hypothesis, 30,000, divided by the given standard deviation, 10,000, over the root of n, 150. I'm going to put all this into my calculator to try and figure out what the z-score is for the sample. Parentheses 32,000 minus 30,000, and parentheses divided by parentheses 10,000 divided by the root of 150 and parentheses. I get this z-score to be 2.449. which then becomes 2.45. So I've now done steps 1 and 2. I've found the null and alternative hypothesis, and I've calculated a test statistic. The next step, finding the p-value of the test, is a little complicated. The first thing I'm going to do is I'm going to look up the p-value associated with 2.45. Again, I need to make sure I'm on the positive side of my table. When I go down the left-hand side to 2.4, and then across that row over to the column 0.05, I get a p-value of 0.9929. What that really represents is, if I have a curve that's centered at 30,000 under the null, and I have a data point at 32,000, this z-score 2.45 tells me that everything to the left here is equal to 0.9929. But that's not really what we're interested in. What we're interested in is what's in this tail here. So to find that, we're going to need to do 1 minus 0.9929, and that's going to give me 0.0071. But I'm not done. This 0.0071 would be correct if I had a greater than alternative hypothesis. When I have a not equal to alternative hypothesis, I have to consider things as extreme on the other side of the table. So really, getting something that's a z-score 2.45 or greater, which is this 0.0071, is the same probability as getting something negative 2.45 or less. For that reason, whenever you have a not equal to alternative hypothesis, after you calculate the p-value, you need to double it. You double it because you're accounting for both sides. If I had instead got a negative p-value or z-score here, that negative z-score would have pointed me to a p-value in the table where I wouldn't have to do 1 minus. I'd just take that p-value and double it for the other side of the table. So it's extremely confusing when you have this not equal to. You need to guide your decisions based off what you get as a z-score. With a positive z-score, do 1 minus the table value, then double it. If you get a negative z-score for a not equal to test, find the p-value in the table. Don't do 1 minus, just take the actual p-value and double it. So in this case, when I double, I get 0.0142. This is the end of step 3, finding the p-value for the test. I now need something to compare it to. I've been given alpha or a level of significance, so the test value, 0.0142, is being compared to alpha, 0.01. When I compare these two, the test probability is greater than alpha. When the test probability is greater than alpha, our conclusion is fail to reject. So step 1, null and alternative. Step 2, calculate test statistic. Step 3, find the p-value of the test. Step 4, compare that p-value of the test to alpha. Step 5, draw a conclusion. Whenever we're drawing a conclusion for my class, the conclusions either reject the null or fail to reject.